Welcome to the second part of section 7-1. If you remember in the last video, we talked about exponential growth, the idea of growing by a certain percentage. And today we're going to talk also about exponential growth, but a very special application of it called compound interest. And I had told you that one of the biggest applications in this chapter is money. Exponential functions model money, and this is a great example of that. So when I talk about compound interest, I'm talking about, you putting money in a bank account and seeing that money grow, or you putting money in the stock market or a bond or some other investment and seeing that money increase. And exponential growth is how that's modeled. So let's start by just remembering real quick the formula that models exponential growth. Y equals the initial amount, 1 plus r, the rate, to the t, where t is time. So my starting value grows by a certain percentage over time. Now, the formula for compound interest is based on this, okay? It's derived from this guy, but it is a little bit different, okay? But you'll notice some striking similarities. So the formula for compound interest looks like this. A equals, now instead of for a lowercase a for initial amount, it's the letter P, 1 plus R over, now a new letter, N, raised to the N times T. So if you look at this, it looks similar, but there's definitely some differences. And let's kind of point those out. Now we know that this right here, in the exponential growth formula, is our initial amount. Well, it's also our initial amount here. But when we talk about money, in the finance world, the initial amount you start with is known by a special name, and that's principal. Principal is your initial amount. And again, specifically, your initial amount of money. Okay, it's called principal. You are already familiar with time. And usually in the money world, that's measured in years. It's very rare that would be measured in anything else, but it could be. And R is the rate. How fast is your money growing? What percentage? And the new one, this variable N, we'll talk about why it's used in a bit. But for now, know that it stands for the number of payments. So N is the number of payments, and you see that N used twice in our equation. So money works on this exponential growth model, but the formula is just a little different. And to see that, let's do an actual example here. So I've got $5,000, and I put it in a bank account. And that bank account pays 5% interest. That means my money is growing by 5%. Now, maybe you've wondered, maybe you haven't, why banks pay you interest. Well, basically, when you put money in your bank account, the bank takes your money and they loan it to people who are buying a car or a house. And when people take out a loan, they have to pay the bank to do that, right? So that's what they pay them interest. So essentially, the banks give loans to make money. And when they pay you interest on your bank account, they're basically paying you a share of what they have made. So in other words, they're paying you for the privilege of loaning your money to someone else. Okay? And by the way, 5% interest in today's day and age is pretty unrealistic. Banks are actually paying a lot less than that, but it'll be a good number to work with. So I've got $5,000 in the bank, 5% interest, and I'm going to let my money sit there for 10 years. It's going to sit there for a decade, and I want to know how much I have at the end when my money is growing 5% per year. And we're going to answer this question a couple of times based upon how often the interest is compounded, and let's talk about what that means. So the first one that I'm going to have us do is if our interest is compounded annually. And annually means once per year. Annually means once per year. So what I'm saying, and I'm going to work off to the side, this isn't part of the problem, but I've got $5,000. And they are going to pay me 5%. And if I math that out, that means that I get $250. And so if I put my $5,000 in the bank on January 1st, on New Year's Day, Then on December 31st, the next New Year's Eve, the bank is going to say, thank you for giving us your money or letting us borrow your money. Here's $250. And my account is not $5,000 anymore. It's $5,250. And then, so that's 1 year. And then we're going to wait another year. And the next year on New Year's Eve, I'm going to get another 5%. Whoops, 0.05. Another 5%. But what I'm going to notice this time is it's not just the 250 again. It is, but it's a little more than that. Now it's my 5,250 times 0.05. And I do a little better. This year, my second year, I get $262.50. So each year, I get a little more interest because each year my interest starts to gain its own interest. So the first year it was just the 5,000 gaining interest. The next year it was the 5,000 plus the first years of interest, 5,250. And so each year I get a little bit better and a little bit better. My money grows by 5% per year. And that's what I mean by compound interest. The interest compounds and earns its own interest. Okay, so I'm going to do that once a year. So let me use my formula. The amount I have, A, is the principal, $5,000, 1 plus, and 5% as a decimal is 0.05. Now, here's where the N comes in my formula. N is the number of payments. The number of payments for A is 1, once per year. So N is a 1 here, and it's a 1 up here. And of course, my time is 10 years. We'll see in the next one that this number will change. Okay, so when you go, you can enter this on your calculator pretty much just like it is. You just use the parentheses. Everything should work out okay. So 5,000. I'm typing it into my calculator. 1 plus 0.05 divided by 1 to the 1 times 10, which is just 10. So to the 10th. And I will end up with, using my calculator, $8,144.47. So in other words, I put $5,000 in, and 10 years from now, I have $8,000. So I gained a little more than $3,000, and I did absolutely nothing. Okay, compound interest. Earned $250 the first year, $262 the next, and so on through the 10 years. But the reality is most banks do not compound the interest annually. They compound it more often than that. And another way to compound the interest would be monthly. And monthly, of course, means 12 times per year. So when I get my interest 12 times per year, I still get 5,000 times 0.05. I'm still going to get my $250. But instead of waiting till the end of the year, instead of waiting till New Year's Eve and getting $250, they're going to do something different. They're going to break that interest into 12 equal parts. And if you take $250 and divide it by 12, you get about, and I'm rounding here just for ease of understanding, I'm going to get about $21 per month. So instead of $250 at the end of the year, I get $21 in January, $21 in February, $21 in March, April, and so on. Now you say, well, probably that should be about the same thing. What's the difference? Well, let's see. So A equals 5,000, 1 plus 0.05. Now, the only thing that's going to be different is my N value is going to change. It is going to be 12 because I am paying 12 times per year. So that's the only difference. I'm gonna give you, and if you look at this, I'm gonna cut your interest rate in 12 parts, but pay you 12 times as often. So I'm cutting your interest by 12, but I'm paying you more often. And basically that's allowing them to do the $21 a month. Now again, you can type this in your calculator just like this, though I do recommend if you do this the exponent on your calculator, you either just say it's 120 or put it in parentheses so you get the right number. Honestly, one of the #1 reasons people mess these guys up is that they just can't get it typed in their calculator right. And so for that reason, it is very important that you do a number of these problems. Otherwise, you may not get them right. Okay, so when I'm done, here's what I end up with. I end up with 8,000, not a surprise, but this is a little different. 235.05 if I round to the cents. Now what I will notice is that from annually to monthly, I have an increase. And that's an interesting thing. You know, if I'm still paying you 5% interest, why is it that I did a little bit better when I compounded monthly? And the simple reason is this. If I get this $21, I don't wait till the end of the year. I get $21 in January, then I've got 11 months to gain interest on it. So the $21 starts working for me right now today. I start getting 11 months of interest on it. I don't have to wait till the next year to start earning interest on my interest. I earn it right now. And so when I compound a little more often, I do a little better. Let's see this bear out. Last one, let's say I compound daily. Okay, this is about as often as I can do it. So that's 365 times per year. So I'm not even going to wait to the end of the month to get my interest. I'm going to get the first chunk of interest on January 2nd, okay, every day. So A equals 5,000, 1 plus 0.05 over 365 to the 365 times 10. And if I do this, and again, I'm just going to put this into my calculator. I'm going to be careful and make sure my exponent's in parentheses here. But if I do this, let's see, 365 to the 365 times 10, I end up with, I don't do a lot better, but I have $8,243.32. And again, a little increase. It's not a huge increase, but it's a little bit because I'm not having to wait till the end of the month or the end of the year to get my interest. I get my little piece of interest right now, and it can immediately start to gain its own interest. So we compounded annually, monthly, and then daily. So compound interest, still exponential growth. But when we deal with money, we add this idea of how often the interest compounds. And you can use this idea to sort of predict what will be in your bank account at the end of a certain period of time, or how your stocks will do, and so on and so forth. So hopefully this makes some sense. If not, make sure you ask me in class tomorrow, and thank you for watching.